Hi, Gary. I only have three windows. How do I get that fourth window to appear again?
Yep. Go up to File,
Yep,
and then New File,
yep,
and then R Script.
R script. All right.
Yep.
Thank you. Yep, perfect.
Yep. So an R script is essentially the window or the file that will contain your code that you write. Okay. And this is the script window. When you open it, you'll see these little tabs, and you can actually have multiple script windows open with different programs if you want, different coding, and you'll just see more and more tabs up here. And in order to, if you save this file, go by going to File and Save, it'll ask you, what the file name is and stuff to save. And then you'll see up on the tab, this untitled one will change to whatever name you saved. So that the upper left will be the script window. Down below is what's known as the console. Whenever you run code, all the code is outputted to this window. And you can also go down to the cursor here, and you can actually type things there and run it from the prompt. So you'll see it as we're running. The upper right-hand window, at least this tab we're on, called Environment. Whenever you run code, you'll be loading information into memory, and a lot of the information telling you the name of the object and how much memory it takes is printed up in the upper right-hand corner. But there are other tabs up here which I don't really use, so I'm not going to go over those. And then at the lower right-hand corner, there's a bunch of tabs for doing different things. When you make a plot, you'll see the graphs being produced out here most of the time, unless you direct it to do something else. You can also, if you go to the tab package window, this will list all the different packages that are you either have downloaded or are included with the base R. So you can scroll down and you can see if you have a particular package and stuff. And then you have a help window. So whenever you ask, and the way to ask for help is you would use a question mark down at the cursor and then the name of the function. A help window will pop up, and this is where all the information for the certain functions that you could be using has definitions of their arguments, and then examples at the bottom of the page, which you can just copy, paste into the script window and run those, and you can see how those work. As I said, you can save a script window just by going up to File and then Save. But let's open one, a script window. So we'll go up to File and Open the file, and then you'll get the window where you have to direct the file, direct it to the folder where you have your file. So go to the, go to your temp and look for the exercise, the R beginners class scripts file. And I get it someplace else. All right, so I'm just calling mine up from a different. And I changed, for all these windows, you can change things like the font size and how the background colors are. And you can go to its tools and global options if you wanted to change the appearance. I just made my fonts big so that you could see what I'm doing. Okay. Did everyone everyone opened their script file? All right, before we get into what all the script is, whenever you write a script, like under slide 13, running scripts line says, you would highlight that section of code that you would want to run. You go up just at the top right of the window and hit run, which will run those, in this example, those 2 lines of code. You can also use Control Enter to do that. And so I've, in the slides that I have slides showing you how to do this and stuff like that. I'm trying to think the best way if I should go back and forth between the slides and the R scripts in the R Studio. So you let me know if you want me to put the slides back up. All right, so all I have to do is highlight a section of code and hit run, and you'll see at the bottom, you'll see the lines that were run and then the results, which we'll get to in a second. All right, so that's the way you would run code. Yeah, I'll get switch back to slides now. So the slides back up. Can you see those? Thumbs up, anyone? Okay, cool. Thanks. All right, so let's first talk about what some of the basic R objects are. And an object is just an entity that you store data in. And there's essentially basically six types of objects that you will create in order to store and manipulate your data. And the first object is just a vector. It's essentially, you can think of it as a single collection of either numbers, characters, and what we'll term logical, which are true and false values that are used within R. And then we have matrices and arrays. A matrix is just a two-dimensional object with rows and columns, and an array, you can actually have more than 2 dimensions. A list will be just essentially a collection of different objects. A list is very handy, and that's what they use in a lot of the functions to do stats and stuff like that. All that information is put in a list, so you can access, you can have multiple objects within a list. So you could have a matrix, you could have a vector, you could have a character vector, all in the same list, and you can access each one of those individually. Then we have factors. A factor is essentially, it's essentially a way of the way they classify discrete values like names and things like that. They can use within functions like that you would do ANOVAs in linear regressions using categorical variables. So you would be coding a lot of that information as a factor. And then the most frequent object you'll be using will be a data frame. And you can think of a data frame as a list, but there's lots of different components that you can have with a data frame. Most likely you will load your data in from like an Excel file or something into R, and it will be all stored in a data frame, and you can there'll be a column for each of the columns you have in Excel that are read in. And so primarily you'll be using data frames. And then the last object is a function. And that's simply just code that's been developed to implement a procedure, like in this slide, like a mean. There's a function for doing means and stuff like that. And you will always recognize a function. It's usually a name followed by parentheses, except of course when you're doing any type of mathematical calculations, you'll have parentheses. But primarily you'll see a function as a name followed by parentheses. So in your R program with that script you just opens. I have all the code that's in these slides associated with each of the slide numbers. So you can just follow along and manipulate and run the code in your scripts if you want to follow what I'm doing. All right, so how do we create our object? And in this example, this is how we would create one, and I call it by hand within the program instead of importing data. The first thing you will do is type in the name of an object. And here, throughout this, all these slides and stuff, I use an object name called data_object. This is essentially the place where all that information will be stored. The next thing you need is what's called an assignment operator, which in my case is the less than and minus sign. Essentially, it looks like an arrow, doesn't it? Just pointing into that object. You can also use an equal sign, but not everywhere in our code. And then if you look at this slide, in the middle is red that if you go to this site and look at this document, it discusses the differences between the arrow and the equal sign. But I'm always used to the arrow sign, so that's what you'll see throughout. So what that assignment operator is saying is that anything after the arrow will be placed into that data object. The next thing you'll see is this function C. It's C with 2 parentheses, so it's a function. This C stands for concatenation. It's the concatenation function. So what happens is, if you place values followed by separated by commas in here, this string of numbers will be assigned to that data object. And the way to see the information in that data object, you can either just type the data object at the prompt, or you can highlight the name and just run it. And you'll see, as in this example, down below the data object by just typing that. This is the way that information is printed out. And this is actually a vector. This is just a single, if you want to think of it as a single row, but it's just a single entity. There's no rows or columns really designating it. So these are numbers. You can also put in characters. And a character has to be surrounded by quotes in order for it to be correct. And that next line just shows you how to do that. There's the specific things you have to do. Let me back up there. There's certain things that an object name can't have in it. You can have upper and lower case letters. You can have digits, but the digit can't be the first character of the name. And if you wanted to make really detailed object names, you can separate words by periods and commas to make the names. But for best practices, you shouldn't really use names that already been defined within R, like some of the function names like mean or length. This is just so you don't get confused when you program. And in R, all the names and anything you do in R is case sensitive. So if you named an object X, a small lowercase x, it's not the same as a large case X. So you have to be careful there when you're programming to make sure you always remember what the object name is and what the case is when you type in code. So that can be confusing. You'll get error messages saying something like, can't find this object. It's usually because you did something wrong. You either didn't load it incorrectly, or it's you created an object name that has a different case. So let's look at the first object, a vector. As I said, it's just a single entity, and you can have collections of numbers in it, as shown up in the upper left there. and I have a data object where I'm storing the numbers 1 through 4 in it, and that's would be known as a numeric vector. Then you can have logical vectors, which are essentially just true false values. And even though it's a character, you just put in T or type the word true, or F for, or type the word false for true and false statements. And then if you look at that object like I'm showing, it shows you what those represent, true, false, true, false. And then we have characters, as I said before. One thing will happen if you combine, as in the bottom example, you have, you put numbers and letters within the same concatenation function. All the numbers will be converted to characters, since that's the standard practice in R. Excuse me. Okay, so when you have numeric vectors, you can do all the mathematical operations that you want on the information. In the upper case, again, I'm assigning numbers 1 through 4 to an object called X. And then I wanted to multiply all those X's within that vector by 2. And all the operations with vectors occur element by element. So in this case, 2 would be multiplied by 1, 2 multiplied by 2, and in that progression. In this example, I'm also assigning the results of that multiplication into another object called Y, and just seeing what's in there, you'll see the values have been multiplied by 2. You can also reassign the computations, the changes back into that original object. So in this second example, when you have X, numbers 1 through 4 multiplied by 2, I can assign that information back into that object. So you'll see X now is 2468. So you lose the original information. So you can just reassign things to the same name. You can, if you have vectors, when you do multiplication, addition, subtraction, whatever, as I mentioned, those operations are done element by element. So in this third example, I have a vector X with numbers 1 through 4. I have another vector Y with numbers 5 through 8. And I'm going to add those together and store it in an object called Z. And the way this works then is then 5 plus 1 is added together, 6 plus 2 is added together, 7 plus 3, et cetera, et cetera. And you'll see when you look at Z vector, the results are correct. So if you do things like this, the vector, the length, the number of elements within the vectors have to be the same. Otherwise, as shown in the fourth example down below, if you have different lengths, then the vector with the shortest length, in this case, vector Y at the bottom only has 3 elements, with vector X has 4. It's going to recycle the vector with the shortest number of elements. So what that means is, if you look at the example in the output below, it's going to add 5 plus 1 is 6, 6 plus 2 is 8, 7 plus 3 is 10, but there's no element in vector Y to multiply against 4. So it's going to go to the top of Y and take that 5 out, use that 5 and multiply it by 4, and you get 9. So be careful when you're doing this stuff. You'll also get an error message that's shown here saying that one is shorter than the other. And that's an indication you did something wrong. So how's that? Is everyone making out okay up to this point? Thumbs up? Yes.
Yeah, so far so good.
Okay, cool. All right, so the next, one of the next objects are that have different dimensions to them will be the matrix and the arrays. In a matrix, everyone knows what a matrix is. It's just an object that will have values in it that you can reference rows and column numbers to get to a specific element within that two-dimensional object. And the first line shows you how to create a matrix. You'll see that there's a name called data, and that's where you would put in within the concatenation function. If this is the way you were doing it by hand, you could just put in a couple of elements, and those elements would be recycled, as in the case of, if you look just below, you'll see that 1 and 2 is recycled all over and over again, 1, 2, 1, 2, 1, 2, 1, 2. Yeah, also in the matrix function, you have to specify the number of rows and the number of columns. And there's an argument that you can change where you can fill in the rows and columns certain ways. So I have it by row is true. So it takes these 1, 2 and go 1, 2, 1, 2 across the first row, and then the second row. You could also just say by row is false, so then it would number in the first column, which the columns are the uppercase, the brackets above the numbers, and the row numbers are on the left on the side of those numbers. If you use by row equals false, then it would fill the matrix starting in column 1 and go 1, 2, 1 in row 1 and 2 in row 2, and keep doing that over and over again. You'll get some errors if, as the example shows here, if you don't have a multiple of the number of rows and columns for which the function would recycle the numbers. So you'll see in this case, this error message comes up, and since it's only 3 values, it gets throws an error because you don't have that 3. They're not, sorry. The 3 is not a multiple of 2 or 4. So it will recycle those values, but then there's a final 3 that's left. You can also fill, you can create matrices with missing values. And in R, whenever you have a missing value, it's coded as an NA. And so in the third example down below, I'm filling this matrix with just missing values, which is just designated as NA. And you can do that by, I use this in when I'm programming to define a matrix ahead of time, the size of it, so then when I'm during the code, I can spit in numbers into those into that matrix, and you don't the speed doesn't slow down. Yeah, and what's that called? Oh, when you're building a matrix, some code you can when you're generating numbers, there's ways in R where you just take the new values and essentially bind them to the matrix, so that matrix grows over time. It gets larger and larger, and that's doing that slows the speed down. And the best way to speed that up is to define the matrix ahead of time, the size of it ahead of time, and then fill the numbers in afterwards. So, hope that makes sense. If you have numeric matrices, you can do all the standard matrix operations as functions for transposing, multiplication, solving to invert the matrix, diagonal function, all that stuff. So that's available in R. Arrays, as I mentioned, it's a separate function from the matrix, but arrays is essentially a way of having data stored in more than 2 dimensions. So in this example, I'm using the array function. I'm using only 3 data points, which will be recycled to fill the array. And I've defined 3 dimensions. The first is the row. So just like the matrix, we'll just have 2 rows in 4 columns, but I have a third dimension, which says make essentially 2 copies of that matrix, and you'll see the result below where you have 2 commas followed by a 1, which designate that first, third dimension, and then comma, comma 2 down below with the second part of that third dimension. And you can see that in this case, you just have doubled, have the same, you have 2 matrices essentially. And you can keep going, you have 4 dimensions, 5 dimensions. It gets confusing though after a while if you program like that to keep track of all that stuff. And then let's see down below where I have. Oh, so you can have arrays. You can have matrices too with characters in them. You just can't do any operations, mathematical operations and stuff like that. So, and you can fill arrays and matrices with logical values, the true or false. So a list. This is a function that's very helpful if you want to keep information from a particular program or coding that you have. You can store it all in one object and keep track of all that stuff. So in this case, I created an object X, which is just numbers, a vector with numbers 1 through 4. Matrix Y, a logical vector named Z with just true and false values. And then I'm using the function list, and by separating the names of the vectors you want to store within this list, I'm saving all that in this vector called Q. And when you type Q at the prompt, or you run just the name, you'll get an image of what's in that list. So here you can see list is, you'll see has for each position of the objects, we'll have these double brackets. So double bracket 1 at the top designates the vector X that we stored in here. And double bracket 2 is the matrix, and double bracket 3 is that logical vector. And you can access each of those within that list by just typing the name of the list and the double brackets and the number that you're interested in, as I'm showing below there. And this becomes important in some programming. Okay, a data frame. This is probably one of the most common objects that you'll be using, because whenever you, as I mentioned earlier, whenever you bring in data from like Excel or a comma delimited file, the data essentially imported and stored as a data frame. And, excuse me, in their particular, you can read about the different restrictions. And the example I have on this slide, I'm creating a data frame storing in object, data object. And you use this function data.frame. And within that, you can put in different, I'm putting in different vectors. And in this case, the way to do that is you have a name, which will be the column name essentially, with an equals and then whatever values you're storing in there for that vector essentially. The next one I have is sex, and that has values M and F for males and females as characters. And then I have whether the name of this vector mature, which I'm just making up, of course. And I have that as a logical vector saying if this fish is mature, it's true. And if it's not mature, then it's false. So when you, as I mentioned, when you read data in from external sources, it usually is turned into a data frame. And we'll discuss this a little bit more. One thing with this tidyverse and the data science being expanded, there's actually a fairly new data frame structure called a tibble, which is used. It has more information embedded within that object, and that's generally used in tidyverse. So you'll see both of these data frames and tibbles being used. And a factor. So a factor is really, you're taking like a categorical variable and coding it so that R knows that it's a categorical variable, and you can use that information in like a notice and linear regression for doing analyses on categorical stuff. So in the example above, I within the function factor, I created a vector X that has the 3 words good, bad, and the ugly, if you're a Clint Eastwood movie fan. And when you show the information in that by typing the data object, you'll get an output that looks like this, where it has this output called levels, and it just shows you the different categories within that's been coded within, that's been coded as a factor. In the example below, I'm just showing how you could use that within a linear regression function, and usually, if you don't create it using the factor function, a lot of the functions like the LMN function for doing linear regression will convert it character names automatically into categorical factors. So if you, in this example, I'm showing Y using numbers 1 through 8 are stored in there. And then I have X for 2 categories, dog and a cat. And because they're characters, this will be converted into a factor. But if they were all numbers, then they wouldn't be. So you would have to be careful about if you wanted to code some numbers as categories, then you'd have to use the factor function. So in this case, I'm just doing essentially, I'm estimating the means for dogs and the means for cats in this example. And maybe we'll have a course later on on how to do some of these things and some of the regression stuff and how to code things a certain way and how to interpret. But in this case, if you look at the estimates down below, the intercept and the mean, when you have 2 categories in this case, the mean for cats is 6.5 here, which if you look at the vector Y, you can calculate that. And then the mean for dog is determined by subtracting the exponent here, -4 from 6.5 to get 2.5, which is the mean for dogs. But that's for another class.
Hi, Gary, quick question.
Yep.
What did you say you had to be careful of if the categories were numbers? Like, so the categories you have here are names, dog, and cat. But what did you say if it were numbers?
Yeah, if you represented a category as a number, like you had stage 1, you just put the number 1 as stage 2. If that's a numeric vector, then the program's going to interpret that as being essentially in a regression. It'll just be a dependent variable, and there'll only be the slope that's being estimated. Whereas if you have a categorical, in the case of linear regression, categorical, it's essentially in ANOVA where you're estimating the means for each of the group, not a slope. Does that make sense?
Yeah, but do you have to put it in parentheses or something so it knows it's a category?
You would have to use the factor function as
the quotation.
Yeah, and you basically take your numbers and store using the factor function stored in this case in X, and then it will know that it should be doing essentially in NOVA. So.
Okay, thank you.
And one of the last objects, as we mentioned, are functions, and usually a function is basically a name with parentheses following it, but within those parentheses are a bunch of arguments that you can use when you for changing certain parameters within the functions. In this case, I'm showing the function for a t-test and all the different arguments within that. So if if you remember some stats, you can do, in this case, two-sided tests by testing means, or you can do whether, hypotheses, whether one is less than or greater than the other. So that's how you would do that. And you can actually write your own functions too. And this is handy when you want to repeat something over and over again and you don't want to calculate the code. You can create the function up above in your code and just keep accessing that function down below. And this is just a really simple example showing how a function is written. And in this case, I'm just we'll square any values inputted and then sum those together. In the way functions work, you'll see this second line with dd. That's just a numeric vector, and then you surround that vector by the function name in the parentheses, and dd is then manipulated as stated in that function, and you get a result of 30. So, yeah, functions are very handy in programming. If you ever want to see the information for a function, if you know the name, you can go down to the prompt and type a question mark followed by the function's name. And in this case, I'm looking at the concatenation function. And this output will be over in the bottom right-hand corner in that window in our studio. And a tab will pop up, will be highlighted, called help. And you'll see these help files come up. And you can, again, scroll down, see different examples. That's a good way of learning, is to, if you're like trying to do linear regression, not familiar, there's examples down below in the help files, and you can copy those and see how the data is being manipulated, or how to correctly code something. So the help files are really helpful. So. Okay, so when you create an object, there are different, I don't want to say attributes because that's actually a function, but the different, I'm going to have to say attributes to each of the objects that you can manipulate and use in some of your computations. So one of the first functions that you can apply to any object is known as the mode. This allows you to determine what type of, in this case, a vector is, what type of vector. So under the function mode on the left, you see the data object 1, 2, 3, 4. And if you type mode, it knows, it sends out this message. It's a numeric vector. So this is important and good for debugging, because sometimes you may have missed a step and in which you didn't have the right mode of a vector. And this is a good way of checking using the mode function. And you can see the other code below just shows you for the different vector types, the logical and the character. You can also do it for a matrix. But when you do it for a data frame, you'll get this at the bottom there. You'll see that the list name is produced, and that's simply because it really is a list. But then you can actually access each of those columns within that data frame and use that mode function, and it'll tell you whether it's numeric, character, whatever. And we'll get to that. I'll show you how to do it. So there's also the length function. So you can use length on any of the objects, and what that essentially does is count how many elements are within the object. But it's different for matrices and data frames. So in the simple cases where you just have the numeric, logical, and character vectors, if you surround length with the object name and run that, you see it just counts how many elements are within that object. Excuse me. when you use length with a matrix, as shown in the fourth example below, it gives you how many elements are actually in that matrix. So this is example, it's a 2x4 matrix, so there's 8 elements. And then if you use it against a data frame, it gives you the number of lists, or in our case, the number of columns. So you have to be careful using the length with the data frame if you're really interested in the length of a particular vector like fish within that data frame. And then we have the attributes function, which is pretty handy to figure out where information within a particular object is. So if you use the attributes function against simple vectors, you'll get these results. In this case, it says null. Essentially, there's no additional information attached to that object. But if you look at like a matrix, what's attached to that object too is the dimensions of that matrix. So that's handy in programming too, where you don't have to use a function to figure out how many rows or columns. You just access that object and the name question mark dim to get the actual matrix dimensions. And then using attributes on a data frame, you'll get all the names of the columns that you have, and it'll tell you under what's called the class that it's a data frame, and then it'll give you actually the number of rows too. So the row name, sorry. And on data frames, you can actually change the row names. Right now, they're just numbers from 1 to 4. So these are very handy functions for debugging and stuff like that. So I mentioned, mode tells you, again, in this example, what type of like vector it is, if it's numeric, logical. Well, you can actually change the mode of data within that object. So, oh, sorry, let me back up. So I'm going to look at 2 functions, the class, which we haven't looked at yet, and mode. So the class function is really handy for determining what type of object it is. So in this case, the matrix, if you look at above with the data object, I created the matrix again. And if you use the class function within that, it tells you it's a matrix or an array. It's a weird, some of the things that they've done to code in R, some information is duplicate. In this case, it is a matrix, but a matrix can be considered an array, so just a 2-dimensional. So you'll get something like that tells you that this is a matrix or an array. In the second example, I actually take that matrix and using an as dot function, you see the as dot followed by the name of, in this case, data dot frame. That will convert that numeric matrix into a data frame. So the difference between a data frame and a matrix is, if you look up above, there are no names for the columns, and you cannot reference the columns within the matrix by names. But when it's converted to a data frame, in this case, then automatically there are names placed above the column so that you can refer to those names, and you can also change those names if you want. So that's a big difference. So if, and we're going to get to how you access the different elements in a second. And oh, down below, this, the second to the bottom code there, where I have a data object as another numeric vector, you can change those numbers to characters using as.character applied to that data object. So those come in handy too for doing certain things. All right, so that was all about creating, stuff by hand. If you and that happens a lot. I bring in data from I just copy data from like stock assessment, I bring it into R, just copy it into concatenate it. And I create, the matrices or whatever. It's just easier to do that. But if not, one thing you can do is, of course, import data into R. And R comes with a package known as FAR, and you probably won't use this since you're using Excel or something. But you can, using package FAR, and you can import all different types of formats, like Minitab. There's a SAS export file, which in SAS, if you have data, you can save it as an export that somebody could use, and it wouldn't be the base SAS files, which are proprietary and you can't actually access without SAS. But I normally import information from Excel, but I sometimes, or most of the time, I just export the Excel spreadsheet as a comma delimited file. So when you're saving, in this case, I have this, you'll see the little snapshot there of 4 columns and 4 rows of an Excel spreadsheet. And when you go to save the Excel spreadsheet, as an example below, you can select save it as comma delimited file. And then you can, as it shows below, you can use the function read.csv to bring in that data set. And one of the things you should do if you're importing data, in the first row, you should have column names for each of the columns. But you can import it without row names. But in the function read.csv, there's an argument called header. And if you don't have any names in those columns, essentially you have to change that to false, or it'll consider the first row the names of the values following. So read.csv is one function for reading in .csv files. And in this function, you actually direct R to the location where your files are. In this case, this is why I had you put all the information in this C/temp file. When you're bringing in files from a particular folder, as in this case, temp, you can't use the backslash as you normally would do to call up certain locations in folders and stuff like that. So notice here in the first example, we have C:/temp/fishdata.csv. So you have to use either the / to designate the different levels of folders, or in the case below, you have to use 2 backslashes to designate the different levels. And the reason you have to do this, because the single backslash is actually used as a formatting character in R when you're formatting tables and stuff like that. So it's either a / single / or 2 backslashes. So you have to be careful there. So why don't you go ahead in this example and load in that either that CSV file and see if you get it. And yeah, let me know if anyone's having trouble. So go up to File, then Open File. Oh, I'm sorry. No, I'm sorry. Don't just use the code, highlight the code, and just run the code. Sorry. I saw 1 thumbs up. Two thumbs up. Okay. And just type run just a data object name, or just type it in next to the prompt down below. You can see the information. So is everyone getting that? I think so. All right. So that's I started doing CSV files because they didn't have any way of bringing in directly from Excel files back then, but now there is. Okay, so this is just an example of showing what you should get. And notice in the data object, the NA, so that is, if you look back, there's actually a missing value at B4 in that Excel table. So that's brought in as a missing value and coded with NA. So you can, there are functions for packages, I should say, for importing Excel files directly, reading directly from those. And in this case, I gave you an example using the package read Excel. So let me get out of there and I'll show you how to import packages. If you're hearing noise in the background here, they're installing our new AC units. All right, so let me just share this. Sorry if it's, tell me if it's too loud and I'll speak up loud. Okay, so everyone can see my RStudio screen soon.
Yep.
Okay, so the way to read in packages, if you go up to Tools at the top and click on that, you'll see the next selection, first selection is Install Packages. So if you click on that, a window will pop up, and this directly reads from the CRAN site where all the different packages are stored. So in our case, we want read XL, and when you type, you'll see all these different names pop up for all these different packages. And so you can either, if you wanted to use the shortcut, just read, you can find all the different packages and use the arrow keys to scroll down to find whatever package you want. We want read Excel. Is that listed? Oh, some don't come up. Never noticed that before. But anyway, you can type read Excel to get that package. And when you click on, you'll click on the name, and then you go down and say install. And this won't require IT support or anything. This is, the packages are stored under your user name account. That in my case, uses under / Gary Nelson. So that's where information is stored that you don't have to worry about. So you always have access now to that read Excel, right?
Hey, Gary, I have just like a general question.
Yeah.
How come a package like that doesn't come already like in R? Why do you have to load those things separately? Just curious.
Probably just manageability, because there's there's hundreds and hundreds of packages on CRAN, and this they have the development committee decided that at some point these are the base packages that come with R.
Okay.
That way you're not overwhelmed with all the different packages which take up memory or space on your hard drive and stuff.
Okay, gotcha. Thank you.
Yeah, and a lot of these packages that are listed aren't even created by the development committee. They're created by other researchers and other statisticians. So. Okay, so in the way, let me get back. Oh no, I'll just do it here. Even though you've loaded a package, it doesn't mean it's in memory so that you can use it. All right, so the way to load a package, and this is in the slides, I show you in the slides, is you type library at the prompt, or it can be up in your code. Which, yeah, it's actually in the code I gave you. And the name of that package. And when you load it, you'll see a message like this. It's loaded, or it's built. This is the first time loaded. And the way to see if your packages are loaded is you can go over to the lower right-hand window. There's a tab called Packages. And if you click on that, you'll know a package is loaded if there's a check in the boxes next to the names. So if we go down to Read Excel, down here, you can see there's a checkbox there. So you can check whether the package is loaded. And if it's not loaded and you don't check this and you try to use a function that's within the package, an error message will come up saying we can't find this function. So that usually means you've got the load. All right, so let me get back to this. All right, so if you look at the example at the bottom of this slide, you'll see I've loaded the package RXL, and you will be using the function that's in the package to read in the data is this function called read_xlxx. And that's the function, and it requires you to provide the location and the name of the Excel file. And then the next argument is the sheet within that file you want to bring in. So if you go, so I did provide you an Excel file with the same name, fish data, same as the fishdata.csv. So why don't you go ahead and run this code, and you'll see that it comes in exactly the same. And let me know give me a thumbs up when you're done running. Okay, cool. This function is a fairly new package, and when you read in that information, it's initially converted to that data structure known as a tibble. Okay, so in this case, I've converted that tibble to just to a straightforward data framing. So you'll see the function as.data.frame. This is converting whatever's read in tibble format into a standard data frame. I mean, if you're using tidyverse, you don't need the data frame, you just use the tibble. All right, let's take a break. How's that? Whoops. Everyone okay so far? Let's take a, I don't know, 6-minute breaks, 5 minutes? Is that okay? All right, be back in 5 minutes. Was that about 5 minutes? I think so. Everyone back?
I'm back.
Thumbs up, everyone? Okay. One more minute. All right. Are there any questions up to this point? No? Okay. I will continue. Okay, I've shown you earlier, just by highlighting the object name and running it, or at the command prompt and typing the name and hitting return, you can view the data. The data that's in there will come up and scroll across the screen. There are other ways in R Studio, in R, to view the data also. Let me stop sharing for a minute. One thing we can do, here we go. Oh, here it is, slide 32, right? Yep. Is you can actually, so in this first line here, I'm just going to load in the data object. I'm going to look at it. That's the data frame. But you can also use this function called view with a capital V. And if you do that, a view of it will come up as a tab in the upper left-hand kind of the script window area. So you can see what's in there. And this is helpful when you have very large data sets, because if you just type the name or you just run the name of the object, if it's very large, you won't see the whole, what's in the whole object, because R automatically stops scrolling at a certain number of rows. So it'll say so many rows are hidden below this or whatever when you do scroll something big. So this is a handy way, and you can scroll down all the rows and stuff like that. I don't use it much because my stuff comes from Excel a lot, and I can see it within that. So what's next?
Hey Gary, is that similar to like you can type names, data, and it'll show you your column headers for your data?
That's just a way of getting the column headers, but this is getting to see the whole data set, all the values that are in it and stuff like that.
Okay.
Yeah, we'll get to the names function a little bit. Let's see. Okay, so that's one way to do it. I don't really use that much. Let me get out of stop sharing again. Oh, wait a minute. Was I sharing that screen? Did you see that on my end? Doesn't look like it. Huh. Okay. No, I didn't. I screwed up. Anyway. Oh, all right. So we're back to the slides. So there's that view command just allows you to show the whole object. But there are ways of just viewing different elements within the objects, okay? And what you'll be using will be in the single bracket notation to access the positions, to state a position of an element within an object they would like to see. So, and as this is for a vector, this is an example for a vector, you can see I created this data object with the numbers 5 through 8 in that object, and you see by viewing it, the name or running the name, you get the output. But what if I only wanted to see what was in position 2? So in a vector, there's positions starting with the first element and going to the last element. So in this example here, I just wanted to see what's in the data object at position 2. So I would use the brackets and put that position number 2 in there, or element 2. And when you hit that, you see only that number 6 is printed. You can also view elements in non-sequential ways. And in the next example, you're using the concatenation function to specify which elements you would like to see in that vector. So separated by columns. So in this example, you wanted to see elements 2 and 4. And when you do that, in turn, you get printed out 6 and 8, because that's position 6 is 2 and position 8 is 4. And one of the special functions, or I'd say function, but symbols you can use in the next example, if you want to examine or examine positions in a hold on a sec. If you want to look at elements that run in a sequential positions, like from position 1 to 3 or whatever, you can use this colon symbol specifying the first element, which in this case is 2, going to the 4th element. And so what that does is create this string of numbers that goes from 2, 3, and 4. It'll specify 2, 3, and 4. And you'll see in the example here, you get the numbers 6, 7, and 8 come out. So that's when in vectors, it's really just a single position that you can specify. But with others, including data frame, you can specify two-dimensional positions and stuff, which we're going to go in next. So this is for matrices, arrays, and data frames. And within each of those objects, we'll be referring to a row, either a row number or a column number, or a row name or a column name. Okay. So in this example, I've loaded that fishdata.xlsx file and printed out what it looks like. And so in this case, we will use the same bracket notation, but in the positions in the brackets, the first position to the left of the first comma specifies the row that you would like to see, and the number following the comma is the column that you would like to see. And that doesn't change. It'll just be rows and columns. The position before the comma and the position after. So in this case, first case, I wanted to see element in row 1, but in position or column number 2. So it would be fish 1 that has a sex in 1. So you can see how that's done. Now, if you wanted to look at multiple rows at once, but this in the single column. So the next specification, in this case, I just did 2:3, so you only get 2 and 3, which is kind of redundant here. I could have used the concatenation function, but that's the way I did it anyway. And what this would do, since anything to the left, again, is the row designation. So we're going to look at rows 2 and 3, but again, in column 2, which is the sex column. And when you do that, the number 2 and the NA are printed out on the screen. Also, another way, again, if you wanted to do non-sequential rows or even columns, because you can use the concatenation function either in the rows or the column position. So in the next column, I wanted to just look at rows 2 and 4, but in column 2 again. So in this case, sex at row 2 is 2, and sex at row 4 is 2. So that's what's printed out. And then you can do all combinations, like I said. So in the next example, I wanted to see rows 2 and 4, but also just columns 2 and 4. And when you do that, you'll see you'll get the sex column for positions 2 and 4, and then the information for the maturity at positions 2 and 4. Does that make sense? There are other ways. In R, you're going to learn there are multiple ways of doing the same thing. And this is another way of producing this, looking at the same information. Okay, so in the next example, I wanted to just look at the elements at row 2 and 4, but I don't have to put the number 2 there. I can also specify the name of that column within quotes. So when you do that, you get the same values as the third example up above when you're just using 2. Another way of showing the elements for particular rows and stuff is, if you looked at the last example, if you use type the data object name followed by a $ and a column name, you can actually access the elements within that column using just the simple notation without the commas designating rows or columns. So in this example, I wanted to look at elements 2 and 4 within column sex. So you get the same values as the example just above. So there's multiple ways you can locate elements within certain positions. And it all depends on, sometimes it just depends on your preference. I don't use the second from the bottom. I don't specify sexes, names of the columns very much within the column position. I usually just use numbers all the time. So, but it all depends on your preference. So not only can you see what's at particular elements, positions, you can actually use the same coding to assign numbers, whatever, to those positions. So in this case, again, we have the data object with the data frame there with the fish information. And you'll see in this example, the second line down, I want to access data object at row 3 in column 2, and I use the assignment operator to put in the number 3. And if you look at position row 3 and 2 up above, so that's row 3 under sex, it's an NA, so it's missing. And I'm going to fill in that missing number with the next line of code. And when you show that object, you'll see that a 3 has been substituted into that position. And this is all this stuff is important for programming if you're going to be doing any high-level programming, because you'll be substituting, you'll be reading values from certain positions, that kind of stuff. So in the next example, it's very similar. If you look at data object, and I'm going to look at rows 2 and 3, I want to substitute something into rows 2 and 3 in column 3. So in, just above, let's see, what is it, column, rows 2 and 3, just in the printout just above here, we see that rows 2 and 3 at position 3 is total length, and we have values of 300 and 456 in those values. And we want to specify, we want to fill in those with the new, or substitute those with new values. Since you are specifying 2 rows here, and you want each of those values to be different, you have to specify this the same. You have to have values for the same number of rows. So in this case, I'm assigning the values 6, 7, 8, and 3, 4, 5 to rows 2 and rows 3. So if you hit the return button and you view the if you run the code and you view it, you'll see that just below position rows 2 and position 3, it's been changed to 678, and row 3 and position 3 has been changed to 345. If you do not include those the same number, I believe it will be recycled in all of those cases. So be careful if you're doing that stuff. Oh, wait a minute. No, I have a note here. Number of new elements must be the same. Oh, okay. Those are replaced. Yeah, so that. And then if we go down below, the next example, we have a data object with the brackets. And you'll notice to the left of the comma, which specifies the rows, the row number, it's blank. And this is how you would specify whether you wanted to substitute or the values within all the rows of a particular column. Leaving that blank specifies all rows. So here I'm going to substitute the number 1 into all rows under column 2, which is the sex. And when you do that, you'll see all of them have been substituted. Although there was a 1 before, but it has been substituted. And then the bottom example, you can also do the same thing as I mentioned, using the different types of ways of specifying columns and the row elements positions. So in the bottom example, I'm in, I wanted to replace row 2 and 4 under sex with the values 999. And when you do that, you can see it's filled in. The 99s are substituted for the 1. So again, these are important. This is really important to learn how to do for manipulating data and doing analyses and things like that. So more examples. You can also, as I said, you can use names to specify what columns, but you can put multiple names within the column. So up above, I'm going to, replace elements in rows 1 and 2 under columns sex and mature. So in this case, you use a concatenation function to specify the columns sex and mature. And again, you have to have the same number of replacement values as you would be replacing. So in this case, there's 2 rows and 2 columns, so you need 4 values to make it work right. And when you do, you'll see below the changes that were made. So before, notice that in the original file here, under the mature column, it's a logical, so it has true false values. But in this case, I took and substituted values 8, 8 into mature, and those aren't logical values. So if you look at the new column, that column has been changed to a numeric column. So you have to be, again, careful doing things like that. And the example just below that, using the mode function, tells you that's numeric. So it's been changed from a logical column, if you will, to now to a numeric column. So be careful there. There's another way of substituting using the bracket, and that's actually using this next example within the brackets for replacing any value within data frame with substituting with a particular value. You can specify something like this, which says within the brackets, use the data object and any values equals. And when you're doing operations, mathematical operations like equals or logical operators using equals, less than signs. Equals is specified by 2 equal signs. So any value within data object equal to 99, replace it with a 0. So that's the whole data frame, as long as it's numeric, of course. All the values numeric. So in this case, you'll see we replaced the sex. Sex under sex, the 99s were all substituted and replaced by 0. You can also, and this is how you would do a lot of different filtering in the next example. If you wanted to filter out certain values that you didn't want to use, this is the way of doing it. So using kind of that example above, but using the commas to designate the row and columns, you can use the data object, the name of the column you want, which is the $, followed by the name of the column, and whatever logical operator you want to use, like equals to 88. And you see there's a comma, so it's looking at any of all the rows within the mature column. And you'll see, oh, I'm sorry, no, when the column's missing, it's looking at all columns, sorry. So what this is doing is trying to find the rows under mature that have 88 in it, but substituting 1 into all of those columns, if that makes sense. So again, so it's looking under mature for the numbers, the rows with numbers 88, and that's in our example above, it's 1 and 2. And then it's going to substitute all the columns. It's going to place a 1 in all those columns. And if you look at the example below, you see that it did across all the columns. And you can use any logical operator. So if you wanted all mature values greater than a certain value, you can use a greater than an equal sign. If you want to use something that's not equal to a particular value, that's specified using exclamation point equals, which are the logical operators as shown below. And you can put different combinations, like if you wanted to say data object mature equals 88 and length is less than 200, you can use these and signs and or signs that you can place in that in the column position to find particular elements under those with those conditions. So any questions up to that? Okay, hearing none. Okay, so that's a way of using the assignment notations. So those are important. So you got to learn these when you program. There's a ways of editing data within the objects, and there is this function called edit that you can use. And in this example here, I have data object signed to edit data object. So what this does, at the bottom you see this window will pop up with that has the red cell outlined cells, and you can access each one of those cells by clicking in it, and you can change the values. So this first line here with data object, edit data object, is once you change those values, then those changes are signed back to that data object. If you don't want to assign or replace the original data object, you can also assign it to another object. So that's not a problem. However, the problem with doing it this way, by changing it during your analysis, is if you do not save what's called the workspace, and that's all the different information that's in memory, and you can do that within RStudio, then the changes would be lost. So I find this kind of, I don't use this as a function at all. So if I have values I want to change, if there's errors, let's say I just go back to the original data and change them. So this is one way. besides the using the notation scripts that we just showed. All right. So let's say you have a data frame as our example there, and we wanted to add columns to it. So let's say in the fish example, I might have an equation that predicts weight from length, and I wanted to add that those weight values to the same data frame. Using, we could use the, in this case, the values under total length as the dependent variable in the regression. But in this case, I'm just going to add a single column. So the example, second example, I'm creating a vector that has the values 1,000, 2,000, 3,000, 4,000, and I'm calling this vector object eggs. So the way you could, there's a couple of ways to attach these. And the first, the most common one, which I'll just tell you how to do that using just this example, is to use this function called cbind. What that means is essentially column bind. Bind the column to the this new column to the data frame. And so you specify that. So I'm going to I want to attach that to the data object and save it. So it's data object assign cbind the object you want to assign that column to, which is in our case data object, and then the next the name of the column you want to bind to that. So once you do that, you can see here that eggs now is part of that data frame. And you can, as in the examples before, if you wanted to just view the eggs column, you can specify data object $eggs, and then that would be printed out at the down in the console. You can do the same. Let's see, what am I doing? Oh yeah. So the next example is just reloading the original file. But another way of adding the column is to take the data object, in our case data underscore object, and specify a name for a new column using $ and then putting the new name. In this case, $eggs. So I wanted to create a new column eggs, and then filling those values. And again, if you don't have the same number, if you don't have values for all the rows, I think you get an error message or it recycles. I can't remember. So in this case, if you look below, again, type the data object, we've created that column of eggs. So two ways you can do this. And this is for adding a column to a matrix. Kind of doing the same thing. So in this case, I only have 2 rows, so I'm just going to add values 5 and 6 in the example. And when you do the cbind, you look at below, and you get this eggs name above that column you just added. Well, previously there are no names in that they can specify. So what this is only a dimension name. So in the example below, just like you could do in data frames, if you use the data object $eggs to view the elements, it comes up with an error message because this is not a column name. It is just it's essentially put a name in the dimension row specification up above. Column, sorry, specification up above. Just put those names. That's why you don't see the brackets, the column brackets that are shown up above in the matrix thing. It just substitutes that dimension name. So that's a difference too. So be careful when you're doing that. The other way is you can attach, add new rows to the data frame and matrix using the function rbind. Rbind is what it does. And here I've created a couple of different objects. I've loaded in the original file up above. I'm calling that data object 1 now. And then I've created a new data frame with different fish numbers and sex numbers. So these are essentially additional fish I want to add into that data frame. They have their own lengths here and then maturities. And so if you look at if you print out data object 2, you'll see that they're different than up above. And you use this rbind command below, where you specify the first object you want to attach the second object to, or row bind the second object to. And when you do that, in this case, I'm saving the rbind to a different object. And you print that out, you can see now you have all the same information for the new fish, but now you have 8 rows, which are the row numbers are shown on the left down below. Okay, so you can do that for both. You don't have to worry about row names or anything for a matrix. You just specify the number of basically a row of numbers, and if you wanted to rbind it to the previous matrix. So there's also things you can do. These are all handy for filtering information, and you can use the bracket notation that we've been discussing to remove certain rows or certain columns. So on the left here, we're going to delete some rows and in a data frame. And remember that anything left of the column specified is related to the rows. So here we read in the fish data again, but we wanted to get rid of rows 2 and 3. So just as before, where we can use a concatenation function to specify which rows we want to see, if you put a minus sign before the concatenation, it will actually remove those rows. So in this case, it's removing all rows 2 and 3 and overall columns. Since the position to the right of that column is blank, it's referring to all columns. So if you look at just below it, when you do that and save it in the same object, rows 2 and 3 are removed. So that's a handy thing to get rid of. You may have rows of data that may be suspect and you want to remove them and stuff. So this is the way of doing that. For a matrix, it's essentially doing the same thing. In the example below, you can see we want to remove just row 2 from a 2-dimensional matrix. And when you do that, you only get 1 row, and it's actually converted to a vector when there's only one row there, unless there's arguments within the matrix statement that you can use not to convert to that. Let's see, and then the same thing on the right, you can also, again, I'm reading in the data again, so changed it. And if you go over to the column position to the right of the column within brackets, then you can do the same thing by removing certain columns. In this example, I'm removing columns 2 and 3, which is sex and total length, and this is the resulting 2 columns. As I stated before, you could use names within that column position to access the different column elements. You can also do that when removing them, and just note in the text right next to that example, you would just enclose the column names separated by parentheses within the concatenation function, and it does the same thing as specifying the column numbers. So again, multiple ways of doing the same thing. And below is just doing the same thing with matrix. Whoops. Sorry. This is removing columns 2 and 4 here, so you get a 2x2 matrix down below. Let's see. Oh, so this is what Dave had mentioned. Oh, yeah. Dave had mentioned this. So we have load in that fish data set, and that's what's specified under change all names there, the first segment there. Let's say you didn't like those column names. Well, you can use this function called names, in parentheses followed by the object, and then assign new names to those positions. So in this case, we're going to substitute ID for fish, sex code for sex, TLMM for the total dot length, and then maturity for mature. And when you do that, you can see in the printout of the data frame below that those names have been changed. You could also change individual column names. This right now just specifies all column names. And so you have to have the same number of names for all those columns, but you can do it individually too. So below, you'll see the example where we kept the data frame that we just changed, but we wanted to change maturity back to mature. So you can use names, the data frame, and then followed by a bracket with the position of that column. So in this case, we're going to change column name maturity at column 4 into mature. And when you, in the example below, when you do that, it's changed back. So you can use the bracket notation to assign names to certain positions of the column names and stuff like that. So I mentioned earlier about using those lines within the row position statement within the data frame to subset or filter certain values out of that data frame. And this is just an example of how you can do that. So we read in the fish data file again, printing it out. That's the standard one. And so here, I'm going to assign the changes that we, or the data we search for within that data object. We're going to assign any of those values back to temp file. And in this case, in the data object, looking under maturity for a value of true. You can either type T as a shortcut for true, or you can type the whole word true. So again, a data object mature is a logical, essentially a logical vector. And when you do that, again, I'm only looking at the condition of maturity be true, but I want to keep all columns so that to the right of the comma, there's no column position. So I'm keeping all the columns. So you can see what happens when you do that. The only row that has a true maturity value in it is row 1. So you only get row 1. And as I mentioned before, the next example just shows you what you can do with more complex subsetting. So in this case, I'm going to keep, I want all the rows that have maturity equal to false and, using the and sign, and any values under total length that are greater than 456. And again, using the column position is blank, so you want to keep all columns. And so when you do that, you get one row, which is row 4. And you can see that's what happens. So this is a handy way of filtering data, manipulating it as we showed. So they're all very related, all these different things. And there is a function called subset, which you would specify similarly as I showed above. Instead, below you have the subset function, followed by the name of the object. And then essentially the same statements up above, except the data frame name is not specified with the $sign before the name of the column. And so you can use that too if you want. So again, multiple ways of doing the same thing. Okay, so sorting, that's always a handy thing to do if you're looking at data. You want to see if there's missing values or some code like a code that's supposed to be in sequential order is there or not. So there's a function called sort, which applies to vectors. You can, oh, sorry, there's two functions. You can use sort or you can use order. That can sort or order can be applied to a vector. So in our example, you see that first object 1 and 2 are out of order, but I wanted to sort those. And I did this, and this sort has this argument called decreasing equals true. So you want to sort it from the highest value to the lowest value. And when you do that, you get 4, 3, 2, 1. And then if you change it to that argument to decreasing equals false, it sorts it by 1, 2, 3, 4. So pretty simple function. I believe the default is decreasing equals 5. One thing I forgot to mention, some of these arguments, there's default settings. So if you don't need to change those, you don't have to specify anything. So if in this case with sort, if I just wanted to sort from the smallest to the largest, I don't have to specify decreasing equals false because that's the default argument. Now, if you wanted to sort data frames, you use the function order only. You can't use sort. So in this case, again, we're reading in the fish data. You can see, again, the values within the data frame. And if you look within the brackets, I'm using the order function within the rows column because it'll be searching down the rows and ordering it by what I specify within the order function. So in this case, I'm specifying data object sex. So I want to order by sex, but also total length. And again, the column will be position will be blank because you want to keep all rows. And when you do that, you can see how that was ordered. So in our base example with the original data, the sex is 1, 2, NA, and then 2. And when we sorted it, now it's 1, 2, 2 missing. But we also had total length in there. So if you look at the original data, the sexes with 2 are in rows 2 and 4, and those values, the length of 300, 539. You can see when it's ordered, you can see that you get sex 1 to 2, and then the lengths have been sorted in the same increasing manner. Increasing order. So if you have multiple, sexes with multiple lengths, it will be ordered within the first column that you specified. So in sex, so if we had another row that had sex equals 1 and a length of 100, then you would see the 2 sexes sorted with 1 and 1, and then the length would be 100 and then 234. So it's so there's different levels that you would sort through. That makes sense. So in merging, so you can actually merge multiple data sets together if that's easy for you to manipulate. So in this, again, I'm creating 2 data objects in this example, the original one. And then in the second one, I'm adding a fish column, which has the exact same fish numbers as in the original object, and the same sexes here, except notice, oh, sorry, let me just back up. So there's only 4 in the original object. And notice now I have 5 within the new object. So there's actually another fish being added to the data set. Excuse me. The sexes will be the same for the first 4, but the new one is 2. And then I wanted to merge these together because I have another column of ages, let's say. So you can see what when you print that out or do that, you can see what the data frame for the second object looks like. So we wanted to merge these together. And since the sex columns and we want to merge them by fish, but we have also the same sex columns, so we want to merge those two because we want to just wind up with an additional age column within the original data. So the way you do this is you use the merge function. The first function, the first data frame that you want to merge the other data into is in the first position, which we will call X in this example. And then you're going to merge object 2 to that. And the next statements is specifying the names of the variables to use as the merging variables. So you'll see the first one is by.x, and that refers back to that first object in that first position. So we want to use names fish and sex. And then the second argument is by.y, and that specifies back to the data object, the second data object. And note, please, that you have to have the same names within each of those two objects in order to merge them. Okay, so we want fish and sex to be in the same. Now, there's other arguments, and you can see these called all.x and all.y. This says that if it's true, if you use all.x is true, then keep all the records regardless whether they could be merged or not. Same with y. So if there are no matching records, you'll still keep all the data. So what happens when you do that? In this example, remember we had an additional fish that wasn't in the original data frame. A new row is actually created. And because the second object didn't have total length or maturity in it, you can see that NAs are substituted into those values. So that's just some of the behavior of this function. Excuse me. Now, if, as in this last example, you used fish and sex to merge the two together. But let's say in both objects you had the same all same columns that you weren't using as the merging column names. So in this case, up or above, again, this is the original data. Object 2 now has total length, which for the first 4 fish are the same as the original, but we're adding the total length of number 5 at 600. And again, we have the ages here. So if you only specify, in this case, down below, fish and sex as the merging columns, look what happens down below. Because they're not merging columns, but the names are the same, it creates 2 separate columns for the first data object specified as X, and then the second data object specified as Y. So you get 2 separate columns. So have to be careful that way too. Any questions up to that point? Shall we take another 5-minute break? Any thumbs up?
Yep.
Okay, let's take another 5-minute break and be back at 20 past 11. On that.
Hey, Gary, can you hear me?
Okay. We're all back. All right. So let's talk a little bit more about some functions that you might be interested in. When you load R, it comes with a pre-installed package called stats. And under the stats, there's a bunch of functions to do standard analysis summary functions like means, medians, sums, that kind of thing. You can apply those to vectors primarily. And when I say that, remember that in a data frame, each of those columns is considered, it is a type of vector because the data frame is actually a list. So in order to apply these functions to a column within a data frame, you have to specify, as we said before, the data frame object and the name of that column. And then the example below on the left is the example for just a simple numeric vector here. Number is 2143, take the mean. And as I mentioned earlier, if you can actually assign the results of these functions to particular objects. So in this case, it's taking the mean of that vector and saving it into another object called temp file. So then you can specify or type the name to show what's in there. So that's really handy to do in programming because a lot of results from regressions and stuff, you may want to use the coefficients to plot a line or something somewhere. So you can extract those coefficients and save it in its own object, and then you have those available to you. On the right is the example for data frame. Again, you have to, down below there, you have to specify the object name, a $sign, and then name, or as the next example shows, or you just specify the column number as in our previous examples. Again, in this second statement with the number 3 column, you can also put the column name in there too, and do the same thing. One thing you'll find with means and stuff, if you have missing values, you will come up with the value produced will be an NA. So an NA, to remove those, is actually an argument within mean called NA.remove, and you say it's equal to true. If you go to the help file for mean, it'll show you the argument, so you can reference that. So you have to be careful of missing values. Now you could apply those vector-based functions to the individual columns, but there's also ways there are functions for manipulating the data frame or even a matrix on a whole. And some of these functions stated below. For instance, you could, if you have a full numeric data frame or a vector, you can sum all those values by rows or columns. You could take the means of all the values within each row. You can do it by columns too. So those functions are available to help summarize things. Oh, yeah, you jumped ahead, but remember the missing values here. Again, as I mentioned before, if you have an NA and you're using functions like the mean, you get an NA produced. So you have to use that argument NA.remove, which is down at the third blue line there showing you where you put it. It's right after the object name that you want to calculate the mean for. And there's some handy functions for summarizing data, doing a general summary. You can use the summary function and apply it to the whole data frame. And in this case, I'm doing it to the fish data frame. And it shows you things like minimum, maximum values if they're numeric. And then some of the category, it'll do like a frequency of the different categorical variables if it's a character or a logical And you can see here below, if you go up to the fourth column that says mature, you can see it's the mode says it's logical, and there's 3 falses and one true value. So you can, but if you wanted to use this function, save the results, you would just put a object before with the arrow before the summary, and it would save all these results into its own object. So anything that produces output, you can save within another object. So keep that in mind. Keep that in mind. And one of my favorite functions down below is called the aggregate function. This allows you to summarize data based on certain levels within a group. So in this case, the first position is for what variable you want to summarize. And in this case, for the data objects, it's total dot length. And again, this is specifying a column in the data frame, but you could also use the data frame and the column number, using the brackets. You can substitute that. That's, again, multiple ways of doing the same thing. And then the next position is the variable you want to summarize, the by variable you want to summarize. And in this case, we want to take the mean of total length for each of the sexes. So you have to specify there's another format for aggregate, and I don't want to get too much into it, but there's different ways of stating the same thing within each of these functions. So I take a particular format and I've stuck with it. So this is the way I do it. And you have to surround the by grouping variables with the term list. And then the last argument, you specify what function you want to use. So you could put a sum there, you could put the mean, median, whatever. And in this case, you can also write your own functions. So if you wanted to calculate the square roots of all the values, or whatever, the square root of the mean or something, you could write a function that includes taking a square root of the mean and stuff like that. And then it would do it for each level of the by variable. So in this case, we're taking the mean by sex. And there are 2 sex variables, variables levels, sorry, 1 and 2. And notice that once you use this function, you no longer get it's specified a particular way. The grouping variable by variable is specified as a group followed by a number, because you can put multiple by variables within that list parenthesis there. You can do it by sex, you can do it by, let's say, maturity, and then they'll have columns specifying each of the levels. So group 1, in this case, it's for the sex, but if you had maturity in there too, it would be group .2. That would represent maturity. And then it gives you the values of that function, but only with a header of X, it'll say X. And you can change those names and stuff like that if you wanted to. And in this case, I saved the results to that object sum file. So. Some other things that may help you in programming. There are what called conditional statements. And then these are statements, for instance, if it's a conditional statement. So if you have, in this example on the left, let's say you have a variable that has 0, and you have a fish that's 3, but you wanted to change that type if the fish is a particular number. So you can use an if statement. It says, in this case, it says if, and the if statement is within parentheses again, because it is a function. If fish is equal to 3, follow and as long as there's only one line, you don't really need these brackets. But if you have multiple values that you want to examine, you have to have these brackets. So it's if fish equals 3, do whatever's in the bracket. So in this case, it's reassigning type 3 to the type variable that was originally 0. Sorry, that's confusing. So it would be if fish equals 3, then assign 3 to that object type. And then below, I just show you what happens when you type that. And on the right's another example. There's if statements and there's if else statements. And so it's the same thing, except after the first bracket, you put else, and then you put another bracket with the other condition. So essentially the first bracket is if the condition is true, so if fish is equal to 3, then do the first position. Else, if it's not, then do the second position. So in this case, fish is 4. So fish is not equal to 3. So we jump over behind the else and we apply the 2 into it. So that could be handy for that's very handy for programming when you're want to substitute values or do other things, only run certain code if a main value is equal to something. So that's very handy. And then another one that I like is the if-else statement. So these are separate. In the example below, you can use the if-else to change values within a position column within a data frame on the fly. So in this case, again, we have the original data object of the fish data. I want to substitute any values of 99 under the column sex. I want to substitute. Oh, I'm sorry. Oops. Sorry to confuse you. So within this if-else statement, there are several positions that you have to have. The first position shown here as the is.na is the condition that you want to examine. All right, so in this case, we're looking within data object sex, and this statement is.na is looking for any missing values within that column. So it says, essentially, you can say this in your head: if an NA is present, then do this, else do not do that. So in this case, we have if there is a missing value in sex specified as an NA, if there is an NA, then substitute the next value, which is 99, put that in its place. If it's not true, then just keep the original value, which is in this third position. I hope that makes sense. And so what I'm doing here, if you look at the whole line, the first statement is I'm reassigning all these new values back into sex. So you take the original sex, we'll be looking in the original data set. If there's a 99, it's going to, an NA is going to replace it with a 99 and assign it back into the original object. So it's changed. So if you look at this example, you see that NA above in the sex column, and then using that statement, you can you'll see it's changed to 99. And what this is handy for is you can have multiple if-else statements within blocked within the same code. So if you want to create a categorical variable from numeric, say you have you wanted to create you have lengths of fish and you wanted to say which is small, which is medium, which is large, you can use 3 of these if-else nested within each other to create the categorical variable out of it. So it's very handy. I find it very handy when I'm programming to do this. And below, oh yeah, this below is an example of how I created a categorical. Well, it's not a character, but I created length bins based on the size of the fish that are in the database. So in this example, I'm adding a new column to the original objects. It's going to be called length.bins. And I'm using the else statement, the if-else statement, to code a 1 if the length is less than 300, less than or equal to 300. Else, I'm coding it as 2. And when you do that, you can see that there's a new column added. So anything below less than or equal to 300 has a 1, and anything above that has a 2. So you can do things like that if you want to make length, frequency, histograms and stuff, things like that. So it's very handy function. I only got a couple more things and we'll stop, and I'll have to schedule another workshop because we haven't even touched on graphics and stuff like that. So I'll do that in the next workshop. So if you're familiar with program, there's terminology called recursion. It's essentially repeating some procedure or function that you wanted to use multiple times and over apply it to certain things. So in normal programming, like in C++, there's for loops and essentially and do loops and stuff like that, so that you use the sandwich code within those statements to repeatedly apply what's within the code. So you can do stuff like that in R, where you can take a function and apply it to different parts of like a data frame or something, you know. So in this example, I'm using this function called apply. So we have a matrix here, 2 by 4 matrix with values 1 and 2 in it. And I created that a function where I'm just squaring the values and then summing them. And so you can create a function or use any function like mean, a sum, or whatever, and you can use it within the supply function. So the first statement, first argument, first position is the object you want to manipulate. And then you have what's the argument margin. So essentially you want to, if you have a 1, it means over the, in that data object, apply that function sum underscore square by rows, or if it's 2, it's by columns. So in this case, I'm showing you applying that sum square over the rows. So if you look at the rows here, you know, all the rows, the first row has all 1 squared, they're all 1, so sum of those together is just 4. And then the 2s, you square those, each one of those is 4, sum those over 4, that's 16. So you can see that it works row by row. If you do it by columns using margin equal 2, the first column would be 1 squared is 1, 2 squared is 4, 1 plus 4 is 5. So you see all of the columns are 5. So that's really handy to, it's a really handy function. And there are other ones for different types of objects, T apply, S apply, so you can look those up, but I always find apply very handy. And the last type of recursion, I call it looping. As I mentioned before, in like C++, Visual Basic, they all have codes for repeating certain codes, and those are for loops or do loops and stuff. So in R, you can do recursion with them like that using the for function. So in this case here, I'm creating a vector, empty vector, and I have a vector with fish lengths. And you can see the for loop here starts, you always start with an argument, a letter that represents the loop, the count over the loop. In this case, I. You have the in statement, and then you specify how many loops you want. So I'm doing 1 to 500. So they're going to do this 500 times essentially. And although this is a little advanced beyond us, beyond this class, in the statement below, there's a function called sample, which you can randomly draw with replacement or without replacement observations. And here, what I'm doing is essentially doing a bootstrap. I'm sampling all those fish lengths with replacement, calculating the means, saving the means, and then if you do the averages and stuff like calculates standard deviation, you can get the bootstraps and stuff like that, means and standard errors. That's just an example. It's a little beyond this class right now. All right, almost done for today anyway. So we've done all these analyses, we got objects, but we want to save the results. We want to print them out, or not print them out, but export them because we want to use the results in something else or whatever. So there's a number of functions you can use embedded within R. There's these functions called write.table or write.csv that you can use to export any of the objects that you create. So in this case, I'm in the upper one, write.table. First position is the object you want to export. Then you have to specify a location and a file name that you want to save the data. And in this case, I'm creating a .csv using by using this argument sep equals comma. So that will put a comma between every variable while it's every element while it's being exported. But there is a function, so you don't have to worry about table. There's a write.csv, so you just specify the object and then the name. So that'll spit it out as another object or comma delimited file, and then you can open that right into Excel, and you'll have your columns and rows specified correctly. But there's also a function, a package called the write.excel package, which allows you to directly output the data object into an Excel file. And this is just the example I am showing, excuse me, showing how to do that. So that's available too. Yeah, so there's lots of ways of exporting data, but these are some of the basic ones. Okay, that was a lot.
Hi, Gary.
Yeah, go ahead, Dave.
Just out of curiosity, why, when you're exporting this data object file, why do you have to have the X equals before the name data object? Why can't you just have data object and then
No,
file?
you can't.
Just curious.
Yeah, no, you can do that. So in functions, in a function, like in a health, let me get out of this and I'll call it an example. All right. Share second screen. Okay. See that? Okay. So if we went to a help file and I wanted to look at, let's say, function, let's do a quick function aggregate. You'll get the help file will list you within the function, the arguments, the names of the arguments you would set a value to. So in this argument for aggregate, the X would be the variable you wanted to summarize or whatever in this case. But within the argument, the position of these arguments matter. So if you knew that the first position should be that object, then you don't need to say X equals that object name. You can just give that object name. However, if you're putting the object name, let's say at the end of that function, you want to specify it last, then you need to specify X equals in this case. So in that example, you don't really need to specify X equals if the data object is within the first position. But if you wanted to, for some reason, put it in the last, that's okay too, but you need to specify the argument name associated with that data object or whatever. Does that make sense? So if you know the positions, that's why some of my functions, I just have data object because I know the position to put that. But if you didn't, if you don't want to follow that or you can't remember, but you remember the argument, then you put the X equals whatever. So in this case, I could have put the file output file name in that first position, but I would still have to have file equals But if I could take their file equals out right now because that's the position of that output file name. So that makes sense. Okay. Let me get back to. Nuts. I accidentally closed this. All right. Sorry. Okay, here we go. Yeah. So again, in this case, you wouldn't have to put in x equals. You could just specify data object because that's where x, the position x would be. So, depends on your preferences. If you can remember, that's great. But sometimes I can't remember, but I remember the argument. So I do that. I think that'll be it for today. That was a lot. I know that. And I'll schedule another workshop to look at graphics. But in the meantime, I put together some exercises that you could do to learn some of this. Let me get out of this again. Oops. Hold on a sec. All right. Okay. All right, so if you go to File, Open, bring up the exercise sizes.r script. You'll see that it'll come up like this. So okay, so I came up with some exercises, and you can use this script, and you can, for instance, the first question or first exercise is to read in this file alewife_counts.xlx, and you can get that from, figure out how to do that from the notes in the lecture today. And so you can just specify the code just below that, so you have a running, you have the code associated with each of those exercises. So just go through for the first 9 of them and try to answer each one of those with code. And so just save your code, once you figured out, have your code there, just save this file. And you'll always have it there. So if there are any questions, we can review it at the next workshop, or you can send me email or something if you have a problem. So try and do each of these things by next time, and see if you can do it. If not, just let me know and I can send you a hint. So that's through 9, and then the 10 through 13 will be related to the graphics. So I'll send out another announcement for the second part of the workshop, and then we'll schedule that, and we can look at the graphic stuff, because that's really a neat part of ours, the quality of the graphics that you can do. It's really cool. I'll have examples of things like Micah has done using spatial stuff. Some of the really neat things you can do. So, are there any questions?
Hi, Gary. This is Scott. I do have a question.
Yeah, hi, Scott.
You mentioned nested if-else statements.
Yep.
Would it be possible to show an example of that?
Yeah, let me think about, I gotta figure out.
I don't know if it's simpler to nest it or just write write it on separate lines is, I guess, my question.
Well, you can do, but it would slow it down because it has to. It'll start again from the top every time you write something. Well, this way it'll go along. It'll assess it row by row, and if it isn't this, then it goes to the next statement. Isn't this? Isn't this? Isn't this? Whereas if you did that each interval row, I believe it'll really slow. Well, it doesn't slow down a lot, but it's not the most efficient way of doing it. But let me, I just got to think a second. Just trying to think. Access. Let's see. Let me see if I can find an example. Something in here. Oh yeah. All right, so I'm just going to paste it so you can see it in this window. So this is something like this is a nested if-else statement. So I'm saying for this in this object VBD, SS stands for sample size. If it's equal to 10 and this type is equal to this, then put a 0 in this new variable called PCH, which is when we get into graphics, it's the size of data, a type of data point. And I just go down here, 10 and type REN, put a 2, 50, put this, blah, blah, blah. And if none of these conditions happen, then just put a 16 in there. So you could do this. You could say if this, but forget how you would have to use the notation, the bracket notation in order to do it. Yeah, you could do it that way. But individually, you need, you would have to, in this case, you could have to put ED TCH, and that would be a single line there. You would have to repeat that for each condition. So from what I understand, this is a more efficient way of doing it nested, as opposed to each individually. Okay.
Thanks. That's super helpful because I just didn't know where the next if else fit in, I guess. So it just goes after the comma and then you hit the next. Okay.
Yeah. So if this statement is not true, then it goes to the next comma, and that's what you put the next if else statement. So it's if else, if else. Yeah, so it can get a little complex there, but
Right. Thank you.
Yeah. Anything else? Well, let me just yeah, we got a little time, 6 minutes, but let me just point out something. Where I am. Let me sober. Oh, I can't do that. Let me share this again. You see that? All right. That's not what I want. If you go to our shared drive, the SharePoint, under Common, I've created a directory, folder for the R users, so anyone can access. Within that, so over the years, a number of us have given seminars and stuff on different R topics, and I managed to find those on the shared drive, and I organize them. And so within the shared drive, there's a folder called courses, and this course is there. So the beginner's art course 2020, but there are others that have been done. Steve Korea and I taught a generalized linear model course for the ASMFC back in 2008. So all the slides, all the code and stuff were in each of these folders. There's a course by John Honig, who did a beginner's course. Brant McAfee, Micah Dean, and I did a spatial workshop on how to use R to do spatial stuff. Mike Magnarski has done an R, beginner's art course. Greg DeSalis recently did a spatial data workshop. So you have access to all these. So you can go and see the different R scripts and slides, if that would help anybody. And then I'm going to start creating other sections where people can share code if they want. So right now there's a graphic script folder, and I've created a subfolder in that called animation, and provided code if you wanted to create some GIF animations that you can put in a slide presentation. So if, I've done a complex case and a simple case. So if you wanted to emphasize, a trend or something, you can have a GIF file that animates each plot being plotted over the x-axis. So that's handy. So keep in mind that we'll be doing stuff like that. So there's some good resources there. But also, going on Google. I tell everyone this: Google is your friend. You can look up anything. Somebody's done it and posted on the web. So if you have questions about, how to change the axis on a plot, you can just type that in R, change axis, and something will come up and help you do that. So there's a lot of good resources now. It wasn't like when I started. So anyway, any other questions? No? Okay. So thanks for coming, and I hope that hopefully it wasn't too overwhelming. But so when you go away, practice, use the exercises, and still and use the slides and the lecture notes or whatever to do them. Just keep at it. Get some other people's code to look at. That helps. That's always helped me in the past to program and see how someone did something. So it's all on you though. So keep doing it. All righty. All right, I'll send out a notice for the next one. Take care.
Thank you.